Hello and good evening. This is Obi-Wan Pez for N Simplex Pachinko. And good evening to everybody out there. Tonight we are going to be doing some more math content on, specifically I was looking at doing some polar graphing and looking at like what is this polar stuff anyway. Um, so it's about that time of the year. I'm starting to get into the last couple of sections at school, and it's always fun times because we don't have time for any of it. Okay, so basically what we are looking at is in doing polar graphing, we are going to be looking at rather than having coordinates in a Cartesian system, which is also called rectangular. We want to look at having our coordinates in polar form, which deal with r and theta. And we talked a little bit about r and theta in terms of trigonometry, and realistically it's the same sort of thing. So this is our polar coordinates. With rectangular form, we get something that looks like this. You get points out in space, which do all sorts of cool things for you. And all of them are measured, or their coordinates are named by using their x and y distances from the origin. So these are all, this is our x distance here, this is our y distance here, and so this one is x comma y. In this case, x is a negative number. It could be -1, -2, -√3, whatever you want it to be. And y in this case is going to be, it doesn't actually matter what it is. It depends on what the scale is. They might be uneven scales, in which case y and x could be literally the same distance despite looking off by a bit. So we get our xy coordinates here. We also then have our polar coordinates, which, if you think of it as if it were at the North Pole. So what you'd see is lines of longitude kind of falling away from you at certain locations or certain angles. So the ones that we find nice are going to be the 45-degree angles. This is like the one thing that I actually wish I had more tools for down at the bottom. Oh wait, I can make straight lines, can't I? I've been doing that for weeks. Oh well. Well, I'm going to have to settle with approximations here. Not that approximate. Not that approximate. Should have just gone with the... My problem is I didn't think it was going to take this long. And apologies for being late, by the way. If anybody actually cared. If anybody actually got the notification, because I didn't. My other account did not get the notification that I was going live. slightly awkward. Didn't get an invitation to my own party. So what we have here are let's go with the main angles here, being our x and y axes. Now normally you don't really pay much attention to these because it's just kind of, they're nice to have, but they're not actually very important in the grand scheme of things, except that they have our most important angles that we like to use. So 0, pi over 2, pi, and 3 pi over 2, or if you prefer 0 degrees, 90 degrees, 180 degrees, 270 degrees. All right. So then what we're doing here is we're saying that at any given point, all right, if you think of our polar coordinates, so you think of, again, if you're standing kind of above the North Pole, you'd see lines of longitude moving away from you like this. I mean, not literally, but you could overlay them on the ground. And then you'd also see lines of latitude, which would be concentric rings going around the pole, equidistant from each other. Again, kind of have to use your imagination here. I'm not super great at the drawing nice shapes thing. And these represent, instead of now angles, these are going to represent distances from the origin. So everywhere along the inner ring here, this is where our r value is equal to 1. And here r is equal to 2, r is equal to 3, r is equal to 4. And the same is true for the angles. We have intermediate angles. Again, here we got pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. These are going to represent all of the important angles that we're going to care about for what we're doing here. As we go out, I have incremented this by pi over 12. So every single one of these going all the way around the entire unit circle is going to be a pi over 12 radian unit. And this also means, or if you prefer 15-degree increment, and this also means that all of the other angles that we're going to care about, the ones that are nice values inside of our sine and cosine functions, those are all going to be represented here. So, as we're looking at different polar coordinates, it is written as r comma theta, which is slightly distracting for me due to the fact that up in Cartesian coordinates, x comma y is usually listed as x comma f of x. So you could have the function value in the second place here being dependent upon the first one. As we get into further stuff, most of the time when you write functions in polar coordinates, they are r of theta is equal to something, which means that essentially what we've done here is now we've got r of theta comma theta. So it's a little bit backwards from how I'm used to doing this for the rest of everything. But, I got over it, so I guess everybody else is going to have to get over it until somebody important comes around and says, you know what, let's switch those. I'm not important enough to make those kinds of decisions, so we have to get somebody who's as awesome as Euler. Might be a while. Although if you are an educational mathematical YouTuber, maybe we can make this happen. Matt Parker. All right, so then we're going to take all these individual coordinates and say, if we have something that says like 3 comma pi, what we're going to do is Either you can read it r and then theta, in which case you go out to r equals 3, and then walk along this ring out until we reach an angle of pi. And this is the point that we get. So 3 comma pi is going to be out here. Alternatively, we could do more of a compass course approach, where we look at the angle first, turn ourselves toward that particular angle, and then start walking in that direction. So turn 2 pi, face this direction, and then walk out 1, 2, 3. So we get to our radius of 3. And once we're out to this point, again, you just plot the point. You can put in 3 comma theta, or 3 comma pi. And additionally, this point has many other names, so it doesn't have to just be 3 comma pi. We could have also gotten here by facing towards 0 and then walking backwards. So walking backwards 3 is going to be a negative 3, and then we could have been facing 0. We could have also been facing 2 pi. So negative 3, 0 or negative 3, 2 pi could have worked. In addition, we could have gone around again and made this 3 comma 3 pi. Or we could have turned in the opposite direction and gone 3 comma negative pi. So all of these points and an infinite number of others are equivalent to 3 comma pi. All those are identically the exact same point. And in polar coordinates, it doesn't actually matter how you get there or when you get there. The idea is that you're going to cover this particular point at some point. So we could plot a whole bunch of other different points and then get all of these and do all that stuff. For right now, though, I do want to... yeah. I'm sure it's going to be awful. Anyway. We're going to just take this whole thing and copy it. Other point and all. And then we're going to come out here and paste it, hopefully at the cursor. Yeah. Cool. All right, so let's zoom in and take this particular point out here, 500%. Whichever. All right, and then we'll take this and we'll do this again. So copy this whole thing again. All right, save that. Good. So we're going to take this and we're going to say if we want to start graphing all sorts of different polar functions, one thing that we might want to do is to try a very simple function. So r of theta is equal to, let's do 2. All right, if we want the function r of theta is equal to 2, this is saying that the r value is going to be 2 regardless of what our theta value is, because there is no theta on this side. Let's see. Okay. So since we have no theta, r is going to be 2. This is kind of like when you did y equals 2 or x equals 3 or something like that in Cartesian coordinates. This would say that our y value is always 2 or our x value is always 3. You want the set of all points where this is going to happen. All right. Sorry. Something's annoying me. That's better. All right. So now that we have this, we want to know where r is equal to 2. Well, that's any point where our r value is 2. So when we go out to theta equals 0 and then r equals 2, we get this point here. When we go to r equals 2 and theta equals pi over 6, we're here, pi over 4, pi over 2, pi, 7 pi over 12, some random number that's in between here, 3 pi over 2, etc. You get the point. This is all of the points on this particular circle with radius 2. And that's totally a circle. All right, so when we draw this in, r equals 2 is just going to get us a circle centered around the origin with a radius of 2. We going? We doing this? There we go. I've been having all sorts of technical difficulties this whole week. It's been great. Cool. All right, so when we take this, move it over, probably not in my face. All right, so then we do something like r of theta equals theta. So this is basically the identity function that we've seen in all the rest of, or in rectangular coordinates, where we had y equals x, right? The output is just equal to the input. In this particular case, our output r is going to be equal to our input theta, but this makes it a little bit weird because the output r is a radial direction and the input theta is an angular direction. So now these are two completely different sorts of things. So because of that, we don't get anything that looks particularly nice. All right, the values that we're going to get here are going to be at 0, we get 0, so that's easy enough. At pi over 12, pi over 12 itself is 0.261, so we're about, that's half, that's about quarter. So it's right about here that we reach pi over 12. Pi over 6 is 0.523, so that is, that's too high. All right. 0.25 is like here. 0.53 is probably closer than that. But whatever, I'm having a hard time reaching that anyway. Right, pi over 4 is going to be 0.785. Oh yeah, that's way off. Anyway, this stuff is really tight in here. It's going to be hard to see. Pi over 3 is going to be 1.04. So this is our pi over 3. It's going to be just past 1. 5 pi over 12 is 1.3. Pi over 2 is going to be 1.57. All right, and then we get 1.83, 2.09, 2.35. These are approximations. Just keep having to tell myself that. 2.61, 2.87, 3.14. Everybody knows pi. All right, 3.40, 3.66. Oops, a little too far there. 3.92 and 4.18. I mean, I'm just going to fill in very approximately where the rest of them are. Four, 5, 6, yeah, give or take. This is going to be at 2 pi, comma 2 pi. And again, 2 pi is very approximately 6.28. So what we end up doing is we get a spiral that looks some things, roughly speaking. Ew. Something roughly speaking like this. It is a nice smooth curve as you go out. And this is going to continue to spiral out forever. If we wanted to go in the negative direction, so this is when theta was from 0 to 2 pi. If we wanted to go in the negative direction, we could also have done that, in which case we would have gone down from 0 to negative pi over 12, and then that would have gotten us a negative number as well, so it would have gone in the other direction. So it would have actually gone back here. And then this would have spiraled out this way through that point as well. Okay, so the red one is specifically when we're going to go from negative 2 pi to 0. I'm kind of committing here. 3.14. All right, you go through here at 3 pi over 2, meet with the other one, and then it would also go out to negative 2 pi, negative 2 pi. This is not particularly a good graph, but again, it's just something quick and dirty that I'm trying to get through so that we can get to the really cool stuff. All right, so from here, we can say, well, all right, this is all well and good. We can come up with anything else we want to do, like come up with a linear function, come up with like a exponential or logarithmic function, all sorts of cool stuff like that. That's great. But it doesn't really necessarily have a lot to do with polar graphing. So polar graphing, for the most part, we want to have this deal with circular functions because we're doing stuff in a sort of circular manner. So we are going to, if we come over here, nope. Is it just position? Is that what it is? Yeah, it's the same position every time. Okay. So if we take this, and if we work off of this in terms of a circular function instead, so let's say the cosine, right? R of theta is equal to the cosine of theta. Then one of the things we can do is come up with a table of values. So do this as theta and r. Right? R is dependent upon theta. And your typical values that we're going to use here are going to be 0, pi over 6, pi over 3, pi over 2. I'm just going to use these. I will, however, fill in the other ones for all multiples of pi over 12. But just multiples of pi over 6 here are easy enough to just do off the top of my head. So hopefully, if you're a trig student, you're going to feel the same way. And if not, you better get there. Don't have a whole lot of time left. All right, 2 pi over 3, 5 pi over 6, and pi. Theta and r starting from 7 pi over 6. 4 pi over 3. Ooh. 3 pi over 2. 5 pi over 3. 11 pi over 6. And 2 pi. So for the cosine function, think of it in terms of what I did a long time ago when we were talking about trig for the first time. Here, this is going to draw in a right triangle inside of the unit circle. The cosine of theta, if this is in fact a unit circle, is equivalent to the horizontal distance across the bottom of this triangle. That is the cosine of theta. Or the cosine of theta is this x distance divided by 1. So it's this x distance. So as this, from 0, from an angle of 0, we're going to get a distance of 1. And then at all of these individual values, we're going to drop to 0 at pi over 2 and hit intermediate values in between. Then at 2 pi over 3, this is going to increase in the negative direction. So then we're going to keep increasing our x value until we reach -1 at pi. And then come around, we're going to reach 0 at 3 pi over 2 and 1 back again at 2 pi. All right, so what are those intermediate values? Well, we're coming down from 1 going to 0. Pi over 6, if you remember the cosine, this is the longer side of a 30, 60, 90 triangle, which is the square root of 3 divided by 2. Pi over 3 is going to be the short side of a 30, 60, 90 triangle, which is 1/2. Then we get 0 at pi over 2. Then we're going in the negative direction, but the reference angles are the same, so this is a -1/2, a negative root 3 over 2, and -1. 7 pi over 6 is going to be, again, negative and large. So this is our negative root 3 over 2. -1/2 for 4 pi over 3. And 0 at 3 pi over 2. This is now positive at 5 pi over 3, and it is also small, so that is 1/2. And 11 pi over 6 is going to be square root of 3 over 2, followed by 2 pi matches with 1. All right, so if we want to graph this on our set of coordinate axes, we get at theta, At theta equals 0, so we're facing directly to the right, we're going to get an r value of 1. Well, this is sort of unfortunate because this is a really small area, so I'm going to renumber. These. So this is going to be 1/2. It's going to be 1. It's going to be 3/2. And this one's going to be 2. You won't necessarily be able to turn every number into every other number, but still. Yeah, it's worth a shot. Yeah, it still looks like it too. Hang on. Yeah, we'll just pop this one out then. Close enough. All right, so at an angle of theta, we get a value for the radius of 1. So we're out to 1 right here. At pi over 6, which is here, 2 lines out, we have a value of root 3 over 2, which is 0.866. So half, 3/4, and that's about, what, 7/8? So we'll call that good enough. At pi over 3, we get a value of 1/2. And at pi over 2, we get a value of 0. So we go back to the origin. In addition, at pi over 4, this value is 0.707. This is the quarter point that I was talking about in previous videos, where we have the square root of 2 over 2 for pi over 4. And also the pi over 12 and 5 pi over 12 are a combination of root 6 and root 2 divided by 4. So in the case of the cosine, the longer one exists at pi over 12, which has a value of root 6 plus root 2 over 4, which is approximately 0.95 or 0.96. At 5 pi over 12, we have root 6 minus root 2 over 4, which is about 1/4. So this creates something that looks like this. And with a more accurate graph, you can see more nuance. It is, in fact, a semicircle. All right, at 2 pi over 3, we try to go 2 pi over 3 this way, but then it tells us to walk backward 1/2. So that's going to be our first point in the down region, unless, of course, you go with 7 pi over 12 is going to have a negative parentheses, root 6 minus root 2 over 4, which is about, again, negative 0.25. 7 pi over 4 is, 3 pi over 4 is going to have a negative root 2 over 2, which is about, again, 0.707, somewhere about here. This was 5 pi over 6 here is negative root 3 over 2, which is 0.866, so we're really close here. And 11 pi over 12 is going to be a negative parentheses root 6 plus root 2 over 4, so that's going to be about negative 0.95. We go through the axis again that way. Nope, that way. We get this stuff. Now keep in mind, we've only made it out to pi. So at pi radians, we had a value of -1, which brought us back here. This is back where we started. And interestingly, if we go to 7 pi over 6, this is then going to drag us backward again to root 3 over 2, which is in exactly the same spot as this point right here. So all of these, are going to retrace the circle. So r of theta equals cosine theta is going to create a circle that is going to get doubled, and it has a radius of 1/2. Unlike our r equals 2 in the above case, which had a radius of 2, in this case our radius ends up getting shrunk down. It's like the whole diameter is 1, essentially. It is. Okay, so what if we want to do sine of theta? Well, if you remember anything from all those trig things that either we did or you did in your class, um, we're going to start at 0 again, but for 0 radians, sine of 0 is 0. Okay, and then pi over 6 is the vertical component to our 30, 60, 90 triangle, which is 1/2. Pi over 3 is 2 pi over 6, which gets us root 3 over 2 for the sine. And pi over 2 gets us 1 for the sine value here. So this is going to start us color code. This is going to start us at 0. At pi over 6 we get 1/2. So we're here. At pi over 3, which is here, we get 0.866 again, which is like here. And halfway in between those at pi over 4, we're going to get the exact same value that this other one had. And then at pi over 2, we get a 1. Okay, continuing, we can see that the sine of theta is going to have the same pattern. It's going to reduce back down to 0 on this side. It's going to have exactly the same numbers as the other ones on the other side did, because these are the height values. All these height values are the same on this right side here as with this left side here. And again, we see exactly the same behavior as with the cosine function, only this is dealing with vertical, like a vertical circle instead of a horizontal circle. So r of theta equals the sine of theta. It's going to put us out here. And again, it's going to go around twice. Right? It's also going to retrace itself. Now again, it's all well and good, Obi, but what about the fact that we don't always get nice just sine and cosine and that's it? Well, that's fine. Ooh. So now we want to check what would happen if we took r equals cosine of theta, and we add 1 to it. Well, in rectangular coordinates, this takes the entire function and then it shoves it up 1 because our function is the y direction. We're trying to find the y direction based on the x direction. So in this case, we can kind of use the same principle. In this case, we're taking the function, the outputs from the cosine that we had below, and we're just going to add 1 to them. But 1 what? So unlike, this is very different from rectangular coordinates. So unlike with rectangular coordinates, this is going to be a radial direction. So all of the distances that our points are going to be away from the origin point are going to be increased by 1. Now keep in mind, it's not the absolute value of cosine of theta. It's actually going to be right, all of the values. So if our values are negative, this means that plus 1, they become less negative. So if we do theta and r again, pi over 6, pi over 3, pi over 2. With 0, again we plug this in, we get a cosine value of 0 is 1. Then we add 1 to it, so it's going to be 2. We take the cosine of pi over 6, which is a root 3 over 2, and then add 1 to it, so 1 plus root 3 over 2. The pi over 3, plug into the cosine, we get 1/2, add 1 to it, it's going to now be 3/2. Pi over 2, we plug that in, we get a 0, we add 1, and we get a 1. All right, rest of the values. 2 pi over 3 is going to be, cosine is a negative 1/2, plus 1 is going to be a positive 1/2 now. 5 pi over 6, plug it into the cosine. 5 pi over 6 is going to be negative root 3 over 2, plus 1 is going to be 1 minus root 3 over 2. Pi at the cosine of pi is going to yield a negative 1, plus 1 is going to yield 0. All right, 7 pi over 6 is going to get us a negative root 3 over 2, and so we're going to see that this is going to just retrace, or rather use the same values as the previous one. So 7 pi over 6, 4 pi over 3, 3 pi over 2, 5 pi over 3, 11 pi over 6, 2 pi. So 4 pi over 3, this is going to be the negative 1/2. Add 1 is a 1/2. 3 pi over 2 is going to be the same as pi over 2, so that's going to be a 1. 5 pi over 3 is going to be the same as pi over 3, so that's going to be a 3/2. 11 pi over 6 is going to become 1 plus root 3 over 2. And 2 pi is going to become 2. So the way this one works, at 0 we get a value of 2. At pi over 6, we get a value of 1 plus root 3 over 2 is 1.866. All right, pi over 3 is going to be 3 halves, so 1.5. Pi over 2 is going to be 1. 2 pi over 3 is a half. Uh, 5 pi over 6 is 1 minus root 3 over 2, so that's 1 minus 0.866 is 0.133, roughly. So it's like way down here. And then pi is 0. Then everything starts working its way out again in exactly the same way. Alright, so this makes this nice sort of round shape, which then goes like that in the middle. This is what is called a cardioid, because it is more or less heart-shaped. Keeping in mind, right, this is not a very accurate picture, but all right, in terms of function transformation, all of these are like when you do y equals a times, nope, some sort of function. In this case, we're doing cosine of b times the quantity x minus c plus d. What we're doing here is we just started adding a d value to the cosine function. We let a and b each be 1 in order to multiply by just the 1, and it changes nothing. And then x minus c, we let c be equal to 0 because we don't want that to change at all either. So when we just change d, this starts making a slightly different shape from the circles that we had initially. So our sine and cosine functions are here. Cosine in red, see that this is going to double up on this particular location. However, when we get a cardioid, we don't double at all. Everything stays positive. All right, now it's also interesting to note what happens when you start changing the value for d. So if you were to go to Desmos, for example, or some other yeah, there we go. Or we go to some other I don't know, can I see this? Yeah, okay. All right, so when I go on to here and I want to do like r equals a cosine parentheses b times x minus, nope, not x, theta minus c plus d. I'm going to add sliders for all four, a, b, c, and d, and return, because no, you totally didn't see that, right? That's, no. All right. So when we just zoom in here, we have a and b each be 1, and we have now the cosine function is causing this to just be two circles, again, overlapping each other at at or in this space. So between 0 and 1 in the horizontal direction. All right, if we increase d to 1, we see that we do get the cardioid shape that was in the other one. And this one's much nicer than the one I can draw, of course. Let's match the color I got on the sheet. Cool. All right, so then what about the intermediate values? So what would have happened if our d value was less than our a value? So we knew what happened when it was 0, it was just a circle. But if we start adding something that's not 0, you notice that we get something that looks like this. Our two circles are not any longer going to be overlapping each other, but one of them is slightly larger than the other. As we can continue to increase this value, as we get close to 1, we start getting a little bit less of a loop in there until it disappears entirely at d equals 1. We get the sharp-edged cusp for the cardioid right here. But all of these values beforehand are also something else. So for this cardioid is where the absolute value of A is less than the absolute value of D. So what happens here is if our A, nope, wrong way. Cool. It's going to be greater than or equal to. Right, so if our D value, no, I had it the right way around. It's okay, I promise. Okay. Try that again. So if our D value is larger, then we start getting this, which is technically still a cardioid. Once we get beyond about 2, we see that this front edge is no longer going to bump inward, like kidney bean or something like that. It's going to just kind of flatten out, more or less be flat along this line. On the other side, this allows us to become slightly more bulbous than a circle is on that side. So you basically are taking away some of the extra distance on this side in exchange for extra distance on the other side. And as we increase the value further, it becomes less obvious that this is in fact a cardioid. This looks like a circle at this point because D is so large and A is so small that the amount of difference that we have ends up only being a 1 that we're taking from one side and giving it to the other, but the radius of this thing is 5, or at least looks like it's 5. So from one side we are going to add 5, and to the other we're going to subtract 5, and the center of this cardioid is still at 0.5. So here. This is still the center of the cardioid. If you measure the distance up and down, you can tell that, yes, in fact it is. So if we did x equals 0.5, oops, right there, the distance up and down is the same. And because we stretch the cardioid in the what is that, positive direction, it ends up having a little bit on top and bottom, which also increase as well as we're starting to move out this way. All right, then if we have anything much larger, again, it looks so much like a circle. You're going to assume it's probably going to assume it's a circle. So anyway, when we have smaller values of d, we start getting this cardioid shape, which is sharper and sharper until it reaches d equals a, at which point, when d and a are the same value, you get this hard cusp that bounces here. Then, as we get smaller values, we get this thing where the two loops of the original two circles kind of pull apart from each other. This is what's called a limaçon. So in a limaçon, we typically get some sort of loop. And typically for this, your a value will be greater than your d value. So if we increase our a value a lot more, again, we're going to get sort of the same thing we did with when we increase d and not a, where you get the two, in this case, the two parts of the limaçon are going to be closer together relative to the whole picture, but they're going to have the exact same distance apart between these two pieces. All right, so then when we start increasing d, we're going to again see that this is going to eventually work itself out. When a equals d, then we get this perfect cardioid with the cusp. And then we can make it a little rounder as we go like that. This really isn't any different than it was before when you decrease your a value and also your d value here. We end up with all the same shapes. It's just a matter of how far zoomed in you are. All right. So there's other stuff we can do with polar graphing, including if we take I can't go up. Okay, we take all this stuff again. Okay. Weird. Take all this stuff, and this time we say, all right, let's try what happens when we take r of theta equals the cosine of 3 theta. Well, this doesn't change the overall value of the cosine function. However, it does change when we hit all those values. So as theta keeps ticking up, and then we're at different locations on the circle, what's going to happen inside is that we're going to receive the same angular values as we would from the original theta, but 3 times faster. So this is our horizontal compression with the rectangular coordinates, so everything gets scrunched inward like this. In this case, it does sort of the same thing, it's just now it's going to get scrunched angularly. So at 0, we still get 1. At pi over 12, we're going to triple it and get pi over 4, which is going to get us root 2 over 2. At pi over 6, we're going to triple this and get pi over 2, which is 0. At pi over 4, we triple this, we get 3 pi over 4, is going to be a negative root 2 over 2. At 5 pi over 6, nope, that's not what I wanted. At pi over 4 becomes pi over 3 is the next one. We end up getting pi, which the cosine value is negative 1. We get 5 pi over 12. Triple it, we get 5 pi over 4, which is a still negative root 2 over 2. Yeah. Forgot what quadrant I was in there for a minute. And then pi over 2. We triple it, it becomes 3 pi over 2, and we get 0. All right, after pi over 2, we get 7 pi over 12. Triplet is 7 pi over 4, which is positive root 2 over 2. Two pi over 3 is going to become 2 pi when we triple it, and then we take the cosine of 2 pi and we get 1. 3 pi over 4. Tripled is 9 pi over 4, which 9 pi over 4 is just going to be in the first quadrant again. So root 2 over 2. 3 pi over 4, next one is 5 pi over 6. Triple it, it becomes 5 pi over 2, where we get a 0 again. Pi over 12. Um, 11 pi over 12 gets tripled to 11 pi over 4. So this is going to be 7, 9, 11 pi over 4 is going to be negative root 2 over 2. And pi here is going to be equal to a negative 1. Triple pi becomes 3 pi. 3 pi and pi are actually in the same place, so that ends up there. And as we continue, we're going to see that 7 pi over 6, nope, 13 pi over 12 is going to be 13 pi over 4 is 7, 9, 11, 13. So that's going to be another negative root 2 over 2. And it's just going to be symmetric to what we have here. So how do we do this? Again, 0 by 1. And you know what? These are all small values, so let's change these again. So this is going to be 1/2, 1, 3/2, 2. Murder on anybody who's red-green colorblind, sorry. All right, so 0, 1 gets us this point here. Pi over 12 by root 2 over 2 gets us somewhere right about here. right in the middle of that number. Pi over 6. So by the time we reach this pi over 6 right here, we should be back to 0. That means we're going to get something that looks, roughly speaking, like this. And then at pi over 4, we're going to get a negative root 2 over 2. So negative 0.707 is like back this way. And so this means that this has to have come through here, connected with this point. And then at pi over 3, we're going to get a negative 1. At 5 pi over 12, 5, that one. 5 pi over 12, we get a negative 0.707 again, so we're here. And then by the time we reach pi over 2, we need to be back to 0. All right, 7 pi over 12, we get root 2 over 2. At 2 pi over 3, we get 1. And by the time we reach 5 pi over 6, we need to be back to 0 again. We're going to get 0.707 at 11 pi over 12, or rather a negative root 2 over 2. And at pi, we're going to get a negative 1, so we are back over here. And again, like I said, once you get to 13 pi over 12, this is going to be a negative value, so it's going to slip you back through onto this point. So it's going to be exactly the same point as this one. So now we're just tracing it over again. We're just tracing over all the same stuff again. All right, this shape here with 3 sort of petal-looking things is called a rose. Roses come in multiple varieties, naturally. You have when b is an odd number, then you're going to trace twice, and number of petals is just equal to whatever your b value is. Again, your b value is the multiplier on the inside of the cosine function. If b is even, then we're going to trace it once. And the number of petals is going to be 2b. Now I should say that these are the number of distinct petals, due to the fact that, right, it's really the same number of petals, it's just that they're, in the case where b is odd, they overlap each other, so you can't actually tell that there are twice as many, unless you shift them a little bit. And this is precisely what happens for all values between the even and odd numbers. You actually can see this in Desmos if we browser. All right, so if we take this and we say, okay, I'm going to alter b, let's change d back to 0. And let's change b up to 3. All right, so we have our rows. And then if we increase b just by like point, right, hang on. We're only sticking between 0 and 2 pi. Right, so if we increase from b equals 3 to b equals 3.1, we can see now that this has been doubled for most of its existence. And in fact, all of its existence. I know that there are 3 lines here, but there's not actually 3 lines there, or curves. It's really that this one drops off when this one picks up. So they have this little cusp part to it. All right, so as b increases little by little, we start seeing that these petals are getting split more and more until we actually get to b equals 4, where we have 8 petals, 4 in the main orthogonal directions and 4 in the diagonal directions. And then we can increase from here. Again, you can see incremental changes, and it traces more and more of this thing until we get to b equals 5, where there are now 5 petals. But if you notice, right, just go back one, they're really just overlapping each other. And then again, for b equals 6, we end up with 12 petals. For b equals 7, we have 7. For b equals 8, we have 16. For b equals 9, we have 18. Nope, we have 9, but they're overlapping. And for 10, we've got 20 individual petals, which are, again, distinct. Now, if you really want to have some fun with this, one of the other things that you can do is change both B and D. Because D, remember, it took like with the limaçon, it took one of the loops and made it smaller, and the other one got bigger because of it. So here, if you increase your D value from 0, you'll notice that the petals do the same. So the overlapping petals now are overlapped, but slightly different size than the other ones. You're going to have much bigger petals and much smaller petals. All right, until we hit d equals 1 when a equals 1, so d equals a, at which point we have those cusps where it hits. Then, if we increase just a little bit more, we actually split the petals up, and you no longer have a flower which has this continual pattern to it like this. It's now going around the outside of the flower. And again, eventually you get out to something that's so rounded. It's kind of like a rouleau. It's just, a rollable, a rollable figure. Naturally, if we increase A, this is going to increase the size of this thing, and then D is, again, going to increase or decrease the size of the individual petals. All right. This does mean that if you get one that's like offset by a bit, and then change your D, this is also going to mess with the size of these things, which are slightly offset from each other. So it's really kind of weird, but I like it. All right, and the only other thing we didn't really talk about was what happens when C is changed. Well, in the case of a circle, our C is changing the initial angle at which we start. So if we look up here, right, theta minus c on the inside of the function is telling us that we're going to change theta by subtracting a c from it. And then if if we want, again, like, c equals 1, this ends up rotating this circle around the origin by a distance of 1 radian. And 1.57 should get us right up to the top, pi over 2. So like I said, we can go all the way around backwards, we can go all the way around forwards. This is just a rotation. So when we have higher b values, this gets a bit more interesting. So here, b equals 2. When we turn our c, this is going to cause us to turn in the counterclockwise direction. And likewise, in the clockwise direction when we go the other way. So you can make all sorts of cool shapes. Almost. Do something like this. And then send them rotating like this. Those of you who are doing like animation, graphic design, that sort of stuff, this may actually be of some interest to you, including game design. Right, you can do all sorts of fun stuff. All right, the other one that was that I sort of just gave away was what happens when d equals 1. Oops. A and d both equal 1, and b is equal to 2. Well, this looks very much like an infinity sign, and actually it is almost an infinity sign. What actually it is if we had r squared, which unfortunately cannot be displayed in this particular format, if we took everything and took the square root of it, then this is what we get. So the square root of a times cosine of b times the quantity, theta minus c, all plus d. Take the square root of all that stuff, and you end up getting the infinity symbol, which is what is called a lemniscate. So the lemniscate is this infinity shape. In this particular case, it is just kind of circles looking. Oh, d. Yeah, d's 1, that's why. When d's 0, that's exactly what we got. So this is the lemniscate shape, which the infinity symbol is. Or if you want, hourglass. All right, you can turn the propeller any way you want. Or give it more pedals. Now, interestingly enough, in this case, right, it is showing you exactly what's going to happen at 1. We just have something that kind of looks like the mushed cardioid from before. At 2, we get that lemniscate, which is the just like 2 pedals. At 3, we get 3 pedals. At 4, we get 4 pedals. It's kind of interesting that this is exactly the number that we had from before. I think maybe because there's no plus or minus. So if we also had the minus version, I think we'd double this. Well, real quick way to tell. Yep. Nothing changed. So yeah, we get the exact same graph. All right, and then again, changing the d value is going to change the behavior of the overall thing. All right, so when d was equal to 0, c was equal to 0, b was equal to 2, and a was equal to 1. This is r squared equals the cosine function, and that gets you the lemniscate. Again, infinity symbol. Righto. So this is going to be, well, this is what my students partially missed um, during this last class period just because we were moving so fast. Um, and here I can take my time. Yeah, unfortunately, we lose a bunch of nuance when we have to do actual like classes within a certain amount of time, all that. So I am looking to put more thought into a scripted video and eventually get those up on my YouTube channel, which is N-Simplex Pachinko. So if anybody wants to stop over there, I have a number of things that are up there now. They're not super great, but at least it's something. And as we go forward, I would like to put more material up on there until I basically have entire courses of material. I still need to get in there and actually do editing and put captions in and you name it, but you know, I'm getting there slowly. All right. Well, call me Blues. How's it going? Or just Blues, I guess. Um, yeah. You have anything you want to talk about? Things are going pretty well. Have some papers to get back to and correct and all that, unfortunately, but you know, life of a teacher never ends. Oops. I've been hanging out on our Discord server, not mine, but the Discord server for math help, and oh man, there are so many interesting characters there. Uh, I've actually got two different servers for homework help, and I think one kind of spurred off of the other. It's kind of interesting, but all right. So let's get rid of the browser. So a lot of this stuff was discovered in and around some same roughly time as Descartes, a little bit after. They started looking at doing polar graphing and trying to get all these interesting shapes and try to figure out what the limits of like different shapes could be. So, what kinds of shapes do we get if we alter particular functions and all sorts of cool stuff like that. Um, Naturally, one of the other things that they would want to do is be able to convert polar functions back into rectangular coordinates. So stuff like, well, even like some of these. So if we had our r equals 5 cosine of 3 theta plus 1, and they wanted to convert this back into a rectangular coordinates, they'd come in and they'd say, well, if you remember, cosine of theta was equal to x over r. You can't mix your variables. Don't do it. Don't do it. So what they'd usually say is, okay, if we can't mix our variables, this is x equals r cosine theta. In this case, we might be able to break up cosine of 3 theta, or we could just say that this is, 5 cosine of alpha plus 1, and now it's just a single variable, which then we can deal with later when we get back to the other side. Maybe not, because that's x. Okay. There's a number of different ways you can resolve stuff. Maybe I'm going to regret this. Yeah, I'm going to regret this. It's fine. Okay, now I'm actually kind of curious how you would do this. So this is, you know what, let's just skip over here for a second. So if this was r equals 5 cosine of theta plus 1, and that's it. Let's just try this. We might be able to, let's see. Could do r squared equals 5r cosine theta plus r. Yeah, that's easy enough. Okay, never mind. I'm just hemming and hawing over nothing, so it's fine. All right, so r squared, if you remember the triangle that we were talking about, was x, y, and r for our angle theta. This means that the Pythagorean identity holds for this as well. So x squared plus y squared equals r squared. Equals 5 times r cosine theta is just x, plus the square root of x squared plus y squared. Because again, right, r is just the square root of r squared. And we're just doing the positive branch for this, not the negative one, because we want something that is actually a function, or at least close. This is not easily done. It is explicit, so we're not really getting anywhere with this. In theory, you could still solve for r, or solve for y. It's just going to be a bit harder in this particular case, and you're probably going to make a couple of absolute values here and there. So, might get kind of gross. So, we might have to settle for implicitly defined. And generally speaking, I'm okay with that. Over here, yeah, this is going to be fun. So this is going to be 5 times 2 cosine squared theta minus 1 is going to be the replacement for the cosine of 2 theta times the cosine of theta. And I think we got too many here. Oh well. Minus 5. This is going to be the sine of theta times the cosine of theta times 2 times the sine of theta plus 1 is equal to r. So as we break this down, this is going to be 10 cosine cubed theta minus 5 cosine theta. This is going to be a minus 10 sine squared cosine theta plus 1. Yeah, okay. So let's multiply by r cubed all the way across. So this is going to get us r to the 4th times r cubed cosine cubed, r cubed cosine, r cubed sine squared cosine, plus r cubed. This means that here we've got x squared plus y squared, parentheses squared, for r to the 4th. Here we've got 10 times, this is r cosine theta all cubed, which is going to be x cubed, minus, this is r cubed cosine, so one r can join with the cosine of theta and become x. Let's make sure we get the 5 in there. And then the other r squared is just going to turn into x squared plus y squared. This isn't nearly as bad as I thought. So this is a minus 10 r squared sine squared theta, r squared sine squared theta is going to become y squared, and r cosine theta is going to become x. Plus r cubed is going to be r times r squared, or parentheses x squared plus y squared. Raised to the 3/2, right? Yeah. Raised to the 3/2 power. So yeah, this isn't too bad. It's easily doable to get it into this form, but beyond here, you're not going anywhere. You might be able to combine a few things. So this, and this are they're in a quadratic relationship to each other. So if we take out 1, they're left with 1/2. Okay, exponents of 0, 1/2, and 1. So that's a quadratic relationship. That's kind of interesting. I don't know if I want to pursue that. Not sure what the hell. Don't have a whole lot of time anyway, right? So if anybody wants to interrupt me, please stop me. Please stop me. So we're going to take x squared plus y squared out from this one is going to leave an x squared plus y squared. This term has an x squared plus y squared, which we can move to the other side. So that's going to be a plus 5x. Maybe not. Yeah, this may not be a quadratic relationship after all. And then here, this is going to move to the other side, so we get a negative. We factor out 1 x squared plus y squared, so we're left with a 1/2 as an exponent. and on the other side you got 10x cubed minus 10xy squared. Yeah, I don't think we're going anywhere with this, so it's fine. If this was just 5, that we would be able to factor it into two pieces. But given that it is a 5x and there's no more x's outside of the variable term I'm calling x squared plus y squared, then yeah, we're not going anywhere with this. So at any rate, it's just fun little idle curiosity and all that. Righto. All right, so I think that might be it for me tonight. Unless anybody has any objections and wants to talk more. Let me look up. Is anybody doing academic stuff? Doesn't look like it. Certainly not live. Okay. So it's a little early for Jason Charles Miller, so unfortunately he's not on quite yet. There is another option.